to present the next speaker. There was one of activities by Sergey Ivanovich. So it was trying to solve the word problem for one related groups, for one related monoids, and well, it's a problem with very simple formulation, and it is still unsolved. So it turns out to be difficult. So Sergey and Victor Guba will speak about this problem. We will speak about the word problem for one related monoids.
Okay, I would like to thank the organizers of this conference, personally Олег Климишев and Igor Lusionek, for inviting me here and for giving me opportunity to give a talk. So let me say some introductory words in the beginning. I'm a former student of Alexander Alshansky in the Moscow State University. And you know that the area of research of Alshansky and Adyanan intersect very much. In particular, I started with constructing some monsters, not some Tarski monsters, but answering some open problems in the group theory, such that if there exists a finitely generated complete group with extracting any roots from any element. And I constructed such an example, being a student. Then I added to that the result about finitely generated simple group, which is not generated by two elements. This was also open problem posed by Weigel. And this was the base of my, the contents of my PhD. And a problem was the following. This research was almost completed when I was a student, a graduate, undergraduate student. And when I went to the other stage, being a graduate student, I did not add much to this research. And actually, I did not know what to do, because the monsters, to construct monsters, this is some interesting subject, but I wanted something else. And I had a problem. And I remember very well that after the defense of my PhD in 1989, I had a long conversation with Sergey Ivanovich Adyan, who was a member of the council of the PhD committee. And he recommended me to read his book on the birth problem. And I got acquainted with this book, and then I went to some other area of research on problems in semi-group theory. So word problems, but not for groups, for semi-groups. This includes the one related monoid case, and this is the subject of my talk, but also I got results about birth-side monoids. If you have an identity x to some power is equal to identically to x to the some power, then whether this problem is solvable, the word problem for this thing. This is very interesting subject, and I think this is one of my best papers in this area. And the only open case now is x squared equals x cubed, very famous problem. This is open. But say if x cubed equals something, then this was solved in one of my papers. Another thing is that I was a visitor and speaker in Adyan's seminar, and this was my favorite seminar because you know, there was some energetic atmosphere, and Sergey Ivanovich could interrupt you during the talk. I like this very much, and for this talk, for the present talk, I also ask people if you want to ask something during the talk, then let me start with the survey of the one relator problem for monoid. We have a presentation with finite number of generators, A1, AM, and single relations U equals V, where U and V are arbitrary words. They can be empty, and this will be one of the cases, and it is solved. And after that, we can assume that U and V are both non-empty. Well, what is the problem itself? We have two kinds of elementary transformations. We can replace a subword U by a subword V in any word, and the same for the inverse operation. And this is illustrated in the picture by transformations of words and also by semi-group diagrams. If we concatenate several diagrams of that kind, then we get an evidence that two words are equal over the presentation. The formal definition is A and B are equal modulo this presentation whenever there exists a finite number of elementary transformations that goes from A to B. And the problem is a real usual kind of word problem, given two words, to decide whether they are equal, equivalent modulo the presentation. It is open, it is a famous problem, but some important partial cases of it were solved mostly by Adyanan and members of his scientific school. Well, so what are the easiest cases of this problem? If two defining words, U and V, are of the same length, then all congruence classes are finite, and then applying relations, we can list these finite sets and to decide whether two words are equal. I have to emphasize that we take U and V and consider an algorithmic problem for these fixed U and V, not uniform, because we don't know if it is decidable. But if you can decide any particular problem, then probably we can have a uniform algorithm, but this is not so important. For the second easy case, let me introduce some definition. A word is hyperprimitive. This is not the only terminology, but this is what was used by Adyanan. If the word cannot not really overlap with itself. You have the picture, you can imagine, and formally it is that no proper prefix of X is a proper suffix of X. And we can assume that U is longer than V because of the first case. So if U is hyperprimitive, then simple to a system for one-side transformation that decreases the length of a word goes to a normal form. It is a very easy lemma. It follows from Newman's Diamond lemma. And in this case, the problem is easily decidable. I will use this terminology hyperprimitive several times, so I wanted to give a formal definition. Now let us start with non-trivial results. There was a long paper, fundamental paper by Adyanan, published in 1966 in МИАН in Russian. And the first result of this paper was the monoid case. What if you have a relation W equals 1? In this case, Adyanan reduced the semigroup, the monoid problem, to the group theoretical result, classical theorem by Magnus, that for one related groups, the word problem is decidable. But the semigroup case differs from the group case because in general, you don't have a group. But suppose that W has some word which is two-sided, so it appears as a prefix and a suffix. In this case, it is easy to see that the word is invertible, and Adyanan subdivided this word into subwords, into a product of subwords, and on these subwords we have a group, and he proved it is non-trivial that if you take this group relation and can solve the word problem for groups, then it implies the solution to the word problem for monoids. I think this result is quite impressive. I know it in very details. There are shorter proofs now based on rewriting systems, but the idea is exactly the same as in the original paper. And so this is a very good result. And the second result from the same paper was non-cancellative case. Now we can assume that two words both are non-empty. Then they have initial letters and they have terminal letters. And if we impose that initial letters of U and V are different, and initial letters, terminal letters of U and V also are different, then it happens that the semigroup, or it's better to say, the monoid presented by this relation is embeddable into the group with the same relation. So if you are embeddable into the group with solvable word problem, this is Magnus, again, then you have the solution of the word problem for the semigroup case. This is also a good result, but I think it is a little bit technically easier because some geometric proofs of this result and even generalization of it are relatively easy. Okay, so here I have an example of non-cancellative words. You see that A is initial, B is initial, so no cancellations. This is a simple concept, C and A at the end. And also, Adyanan proved that divisibility problems are also decidable. Okay. The next result I want to mention is a joint result by Adyanan and his student Grigor Oganesyan from Yerevan. He works in Yerevan now. There are several interesting theorems in this paper, but I will mention only a few of them. Well, first is the reduction of the general word problem to the case of two generators. Assume that we can solve the word problem for the case of two generated semigroup with generators A and B. Then it happens that the general word problem also can be solvable. Well, now let us consider the case when the relation is cancellative from both sides. So the initial letters of U and V are equal, and the terminal letters of U and V also are equal. This case was reduced, not solved, but reduced to the case when the relation is has no cancellations from at least one side. Therefore, we can assume that we have two words on B and A and reduce everything to the following open cases. BPA equals AQA. This is the basic case. P and Q are any words. And in some cases, the right-hand side can consist of one letter. This is a special case, BQA equals A. It is very, very interesting, but it is open. In some paper by Oganesyan, I will tell it later, this problem was considered as a solved one, but it was based on a wrong result. I will review that later. Okay, so we have two generators, and this case when we have non-cancellative left letters and cancellative right letters. This is what is the subject of the present research. Well, and also this paper contained some results, and you see U and V, U is longer, V is shorter, but when V is hyperprimitive, the short word, and is contained in U, then also they proved the word problem is decidable. Okay, now let me introduce the concepts of left and right graphs of semi-group presentations. These concepts were introduced by Adyanan in one of his papers. These are quite easy notions, but very convenient. So let us take an arbitrary semi-group presentation. All words are non-empty, and construct a graph with m vertices, that they are just letters, and n edges. Each edge corresponds to a relation. The construction is as follows. We take a relation, take its initial letters, the left letters, and connect it with an arc. If there are several arcs, this is okay, so the graph is not necessarily simple. And this gives us a left graph of presentation, and similarly, if we connect by an arc terminal letters of a word, we also have the right graph. Well, so let me illustrate it by the following example. We take free commutative semigroup on 3 letters, and the left and right graphs are triangles. It is easy from the picture. And this is some artificial example with some random example, A, B, C, D generators and 3 relators. And then for the left graph, we have a chain. And it is important this graph has no cycles. And the right graph has cycles. In this case, it is a loop. You see the C and C here on the right. This is a loop. If we have no cycles, this is a good thing. And remember, I will recall that for this case, BPA equals AQA, you have only one arc between B and A, and therefore we have a left graph without cycles. Sorry. Okay, this is the next page. So there is a famous problem, some kind of generalization. It is the answer is unknown, and not so many people try to solve it. But this was posed also by Adyanan. Suppose that you have a left cycle-free presentation. Does it imply that the word problem is decidable? Not only word problem, but also divisibility problem. Left divisibility problem. It obviously implies the word problem. If we can do something with divisibility, then the word problem is solvable by the following algorithm. Take a word starting with A, and we want to find out if this word is less divisible by some other word starting with the letter D. And if we know the answer is positive, we can find effectively the quotient and then continue dividing by other letters of this word. So we decide whether a word starting with A is less divisible by D. From A to D, we have a single reduced path in the graph. Therefore, we can guess what are the cells in the semi-group diagram between A and D, and we can insert them. I retell it into geometric language. Of course, in the papers by Adyanan, it was in just combinatorial terms, word transformation. So when we insert them, we have an angle, this is a question mark, between some word that goes after A and some other letter, and we continue in this way. And this process is deterministic, and if it terminates, then we know the answer to the divisibility problem and also know the quotient. And this is a very convenient thing. It is called an algorithm A. In some equivalent version. This was published in 1976, published in Algebra and Logica, Algebra and Logic. This is an issue, very famous issue from Novosibirsk. Okay, in this example, I take the relation ABA equals BA. You have not a hyperprimitive word, so on the left hand side, and decide whether, say, a word ABAA is left divisible by a letter B. And we know definitely what happens in this reduced diagram between A and B, how to feel this angle. We take this cell, and after that we have to feel the angle between A and BA, and this can be done easily. A, in some word, which is dashed word in this picture, equals this BA. And so we have the positive answer about the question of divisibility. One more example, this special case with BQA equals A. We decide if BA cubed is left divisible by A, then we insert this diagram and then continue in this way. Also the answer yes. And this is a very interesting algorithm. Actually, you can take any presentation or even one related presentation and then try to do what happens with this picture. Does it repeat itself somehow? In this case, we can have a proof that the process is infinite, or it may have some interesting behavior. What happens in general? Less is known in this area, and I invite those who want to implement this to study this interesting algorithm, Adyana's algorithm, algorithm A. Here I illustrate the algorithm one more. So we have a word, and we have a letter A. We find the path in the left cycle graph, and we know the first cell in this diagram if it exists. Then after that we have a next angle and insert the second cell, and this is unique. And if we go to the end of the word with some additional portion, then the answer is no. The word is not divisible by A. But what happens if we continue this process and have a cell that has contiguity, complete contiguity to the upper bound W, labeled by W? Then the algorithm finds the first transformation of the word. We don't know if the diagram exists, but if it exists, then it definitely starts with this cell. And then we can continue to transform this. Also, this is the original algorithm A. This is the algorithm is the original form. So it actually works with some word, and in one case it can terminate with negative answer, and in one case you have possibly infinite sequence of transformations of a word. And what happens with this word? What is the behavior of this algorithm? This is very, very interesting. So we now ask, can algorithm A have complicated behavior? If yes, then there is a chance to construct a Turing machine, a general Turing machine, based on this A algorithm. This is a way how to solve the problem in the negative direction if this answer is true. So you need to find a complicated word, such that this algorithm A has a very complicated behavior and simulates a Turing machine. And if not, then we can then we know how the algorithm works, and then this will solve the problem in positive. I know only one paper of a student, a woman from Paris, and I had some handwritten notes. This was probably her master's thesis or something else. the name is Bousma, probably this is a Dutch name. And it was a paper where she gave examples of applying algorithm A to some word. I don't remember what was the presentation. It was cycle-free, but I don't know the form. And algorithm A had this feature. Usually, if you take some arbitrary example, and if this algorithm has a long process, then you have this pumping on one place. And she gave an example when the algorithm is a bit more complicated. It can have pumpings in two places. And this paper was written probably in the beginning of maybe 90s. And after that, I didn't hear any new results in this direction. And I have to mention that this is also interesting. Well, now let us discuss the special case BQA equals A. In this case, you have a deterministic process that I would like to present in more detail. You compare words bx and by, whether they are equal or whether one of them is divisible by the other. And if they start with the same letter, you can simply cancel this letter for B and for A. And what happens if we compare BX and AY? We have to replace this A by BQA such that the word, the second word, will start with B and then we cancel B. So it goes to BX, the relation BQA-Y, then cancel B and go to X, QAY. And this process is deterministic. Also, this is some analog of the algorithm A, some implementation of it. And the process stops if one of the words becomes empty. In some cases, one can prove that the process is infinite if you try to fill some angle, and then if you get to the same angle in the result. And this is an example of an infinite program that never terminates. But also you can think that sometimes probably the behavior of this algorithm can be more complicated. So the question is, can the word Q be so smart that it will contain the full information about Turing machines? This is not known. Okay, now let me illustrate it in dyadic numbers. A is replaced by the dyadic 1 and B is replaced by dyadic 0. Then the transformation 0x0y or 1x1y means that if M and N have the same parity, then we can divide them by 2, integer, division by 2. And this is one transformation. And if they have different parity, then if the first number is even, the second is odd, then it is visible from this scheme where the dyadic is from right to left. Then one word is divisible by 2, and the other number goes to, here in this example, by 69 plus 11. This is an arithmetic progression. And what does it resemble? This is some kind of 3x plus 1 problem. This is famous problem. Everybody knows what is the water-colored problem, it is called, or something. There are some other notions. If an integer, natural number, is odd, then we send it to 3x plus 1. If it is even, then we send it to x divided by 2. And it is not known whether any natural number goes to 1 after a finite number of steps. Say for the number 27, we have more than 100 steps, and this sequence goes through 9,000 something, and then goes to 1. And nobody knows that this problem is considered as an extremely difficult one. And this is of the same kind. What I demonstrated before is the same problem with pairs of numbers and a transformation of this kind. So let me now mention the result by John Conway, who invented the game Life and other things. By the way, he died in this April this year in the United States. So he had a paper named Unpredictable Iteration, published in 1972. And here you have a number of transformations that depend on the residue of x modulo some number p. Like here you have even or odd p equals 2. And a naught b naught, a1 b1 are some rational numbers such that the result is always integer. So this is a generalization of the 3x plus 1 problem, is motivated by this problem. And Conway constructed some schemes like that, showing that for them the analog of the 3x plus 1 problem is undecidable. So we also ask if the finite number of iteration can reach 1, and we can decide that algorithmically. Therefore, we can ask, can one relator problem, or some of its generalizations, like cycle-free divisibility problem, be undecidable? And I think that probably yes. Almost all people who worked in this direction tried to solve this problem. But Sergei Ivanovich Adyan is one of private communications mentioned that it may be unsolvable. And as an argument, he recalled the result due to Yuri Matyasievich obtained in 1967, so before the famous 10th Hilbert problem. And this result is not exceeded so far. It states that there is a semi-group presentation with 3 defining relations and unsolvable, undecidable word problem. In this example, one relation is very long. Defining relators have length about 1000, and it contains the information about the universal Turing machine. And 2 relations are very short, length 3, 4, 5 of the word, so it is very close to one relator. And this was mentioned by Adyanan, and I would like to recall this remark. It is not a very popular idea. I don't know examples in a written form that someone conjectured that probably we can try to solve this problem negatively. Who knows? And after that, let me mention some more results from the same area, and all of them are the last results mentioned here are from the end of 19th. And there is also a short paper by Adyanin published in mat-net in 2004, and that's all. About 15 or more than 15 years, no new results in this area, which is a bit strange. Now, what are other results on this area? For the case BQA equals A, there was a paper by, even 2 papers by Aganisyan, and who reduced the word problem for this case to the divisibility problem for cycle-free presentation. So you have no left cycles and no right cycles. And in the paper by Asanna Sarkisyan, there was proof of this result that for cycle-free presentation you have decidable divisibility problems. Unfortunately, the paper was had a gap, and Adyanan mentioned in one of his papers, and this result is not proved, and then all results based on the theorem are conditional. So the case is open. This case is open, as I mentioned. And the next thing is in one of my papers, I also studied this case and show that three problems are equivalent: the word problem, the divisibility problem, left divisibility, and the right divisibility. When you have cancellations, I got a talk on the Adyanan seminar, and Adyanan mentioned that the result about right divisibility is quite unexpected. It is also equivalent. What is an idea here? Left divisibility always implies the word problem, the equality, and in general it is harder because it is a kind of membership problem, and membership problems can be sometimes undecidable. So this result, in fact, shows that the word problem is not so easy as it can be. And also there is a person from France, Guillaume Vati. I know him personally. He's a computer scientist, and sometimes he went to this area and presented the paper where U equals V. U is much longer than V, and the V is hyperprimitive, like in Adyanan paper. But in their paper, V was contained in U, but generally it is not contained. And Guillaume Veti, using A algorithm, studied this case. I remember that I read this paper in detail. This was a quite good paper. And after that, Adyanan visited Paris, got acquainted to Guillaume Veti, and showed me the preprint with very a lot of red remarks on the margins, and said, "This is me reading." Okay, so he was very careful about style of writing, you know, and this was mentioned in yesterday's memory evening. Okay, let me finish on that. Thank you very much for the attention. I am ready to answer questions, if any.
So, other questions?
May I ask a speculative question?
Mm-hmm.
So you mentioned this interesting analogy between this 3x plus 1 problem and this problem, or let's say the question of termination of algorithm A. Can we make perhaps this analogy more formal in the following sense? Suppose we sort of reduce the 3x plus 1. Can we reduce the 3x plus 1 problem formally to the solution of one relator?
Oh yes, the question is very clear. I think that it is difficult to simulate directly the 3x plus 1 problem into the word problems or divisibility problems, because you have here the base 3 and the base 2 different numbers. In my case, you divide by 2 and you multiply by some power of 2. This is a different case. But if you have many relations, maybe you have some chances to have more complicated system. But I'm not really sure about the 3x plus 1 problem in the language of word problems. For instance, this is a very natural idea, but I don't know any construction that can lead to numbers. Also, I cannot deny that it is impossible. I cannot deny that it is possible.
Okay, thank you. Yes.
So I have a question. So as far as I can understand from your talk, you have no guess, you have no real feeling. Is the problem positive or negative? So is it correct?
No, in some cases, like maybe some Fermat theorem or twin prime theorem, everybody knows that the answer has to be yes. But in this case, I tried to emphasize that the answer also can be negative. I don't have any definite impression, but I admit both options. The same for the amenability problem for F.
Okay. And okay, it looks like there are no essential progress for last 20 years, right?
Yes, the results stopped to grow at the middle of 90s. And also there is the paper by Adyanan published in the beginning of 2000 something. It was based on an old result. He told me that he just wanted to publish it because it was mentioned somewhere or something like that. But this is also not a new result and not very general.
So nobody has really beaten Adyanan here, right?
Yes, yes.
There are some questions in the chat that you might want to read.
I did not see in my screen. Yeah, I don't have. Oh, probably I will get to the chat somehow.
Actually, I can read it.
Oh, yes.
So that's the first question from John. Okay, that's no real name. In view of an apparent gap in Sarkisian paper, do we know whether the word problem for groups that are left and right cycle free is decidable?
Okay, let me, now I have this access to chat. Let me try to, the question by Ben Stenberg, right?
No,
the previous one.
From John.
I guess this is John Meakin.
Okay,
might be the John.
Yes.
This is in view of an apparent gap in Sarkisian paper. This question, yes?
Yes.
Do we know the word problem for groups that are less? No, nothing is known because this is unknown. For groups, for semi-groups, I think this is almost the same, and probably one can even show that for positive words, it is equivalent. So even if you know the answer for semi-groups, then for groups, it is also either equivalent or more complicated. But the gap is very serious. I read this paper. The story is the following. Adyanan told me that the referee was Makanin, and I trusted him. So the paper in details, and so the gap was found by Aganesian, by the way, who referred to this paper and then revised it and found out that Sarkisian had a mistake. Also, other questions from the chat, I need to read them. Was it this problem on which Magnus said the solution is positive on even days and negative on odd days? Well, I remember this. I did not know that this is Magnus, but this is often attributed to the amenability problem for F. For the one-related problem, there is only probably one can try to solve this problem in a negative direction also. If you go back to group, what is the minimal number of relators for a group with undecidable word problem? I guess that for two relations we have no example, and this is a problem mentioned in Kaurovka notebook. One relator case is solved, and two relator cases is unknown.
Here is the answer by Steinberg that it is 12.
I don't know
Currently, well, I mean, the best we know so far.
Can you give one related semigroups with no finite complete rewriting system? This is a question from Ben Steinberg. Well, it is a very famous problem. Of course, nobody knows anything from that. I remember I discussed it with Steve Pride. This is complicated. For finite complete presentation for one related semigroups or groups, nothing is known. By the way, for some particular cases of PQ equals A, I constructed some interesting complete presentations, but this was every construction was personal for this particular semigroup, and finding normal form, finding ordering in general, it is unknown and it is complicated. Is anything known about semi-two systems with one reductions? I remember that very regularly some open questions in this area, probably open, but I don't know details. If it is one-sided, then something is known, but I don't have a clear list of known and unknown results in this area.
Okay, other more questions?
Here, Alexei Talambuts also mentions that the algorithm A was published in Theoretical Computer Science because in 2005. Yes, I know this publication. It repeats the Algebra and Logica paper in Russian because the algorithm is still important. And so it was decided to publish it in English.
Okay, there's a message by John, so everybody can read it. It's not a question. Okay.